All right, so happy Wednesday, everyone. Morning. Thank you for coming. Today we start off with some more machine learning, namely random forests and decision trees. We'll go over your home assignment, and perhaps you have any questions from the lecture pertaining random forest and decision trees or entropy or something from previous weeks. Please feel free uh, to let me know. So, you guys can hear me well? I had a micro problem. Hello? Anyone here?
Yeah, we can hear you well.
Sure, okay, thanks. So, let me open up the lecture real quick. Let's just briefly review what have you. Visualization, position boundary. Oh, something happened. Okay, hopefully that was not visible. Probably was. So how to build decision tree. So you went over entropy, information gain. All right, I see. Examples. What's in here? Lots of examples, of course. Okay, D3, more decision trees, algos, or something that was actually relevant before them. Ensembles. Weighted averaging, stacking. This is actually kind of important. Conceptually, ensembles is something that was very prevalent in the era of Kaggle back in 2017, 2018. And every single participant in every competition with tabular data was using Kaggle. Kaggle's best strategy, like state of the art, to blend as many trees and like boost things as possible. And it's kind of a vital thing for both like competitions, kind of like hackathons and stuff like that, as well as your potential current or future employment uh, in industry or in business. If you are dealing with tabular data like decision trees, and namely something more advanced called gradient boosting, we'll probably go over that later. Is like the best way to literally approximate any to squeeze out the best possible outcome, the best possible performance metric from your data set, from your task. And this is why ensembling is quite a thing to pay attention to, especially like during this course. And as use cases are just very broad. Basically, you once again, I do have a question. You went through the whole lecture, or not? Can you clarify on this? Have you seen these slides and something like all the way till the end, or something was left out? That was the question. Hmm. Well, I'll take that as if you've basically finished all the slides. So once I'll just briefly reiterate, ensembling is like a very cool technique to combine many weak, not necessarily weak, but like diversified predictors, independent models. Namely, like here they have this H denotion for model. You combine them in some way, you average them, or you do some voting classifier on top of them, and you retrieve, and as a result, much better, more resilient model, which is like less biased and has probably less variance, hopefully. This is the idea. Most methods to classify, to ensemble like decision trees or different algorithms, any kind of ensembling technique involves reducing either variance, which is rarer, more rare, or reducing bias. And by bias, they usually just tend to create as many like independent, less least correlated models that have like good description of certain parts of the data set, and then combine them together, fuse them and merge them together, and in the end I get this like good predictor h capital of x. And they basically show that if we go once again briefly over ensembling, there is this weighted averaging. Basically, you have L models, and each of the models has its certain amount of input in the final score like metric for your performance. And this weight is basically something on the range from 0 to 1. And all the weights from your ensemble should sum up to 1. Meaning you have like if you have 10 models, a typical weighted averaging, like not a typical weighted balanced averaging, would mean that each model contributes equally, like 0.1 contribution of the final score. But sometimes that is not the best case to like combine your results and your performance evaluation, and you need to give preference to one model, give more preference to certain model, whereas like taking some of the weight from the other model. Say you have like a very powerful ensemble of XGBoost and 2 light GBMs, and it's probably overfitting a little bit, ever so slightly. And you have another model which is basically a very refined and consistent, slightly less powerful, but still well-trained light GBM. Light GBM actually boost, once again, these are the gradient boostings. This is just a brief example, like pops into my head. So you have this one strong, powerful ensemble, which is already an ensemble itself. Like, doesn't matter what's inside there. Just two extra boost, one extra boost into light GBMs, 3 models. And you have additional specific separate model, which was trained in a more like restrained way, which performs slightly poorer, but still it's quite consistent. And you decide to combine these two models to an even bigger ensemble. This is like kind of a stacking paradigm, but it's not quite stacking. So you just combine these two models with the weighted averaging. And you have these models. Let me pull up Paint. Have these models. Let's see. Okay, how do I do this? So you have XGBoost, which is like one of the most powerful tools and still yet existing in data science community for tabular data. And you have 2 times light GBM. I should not do this because this might confuse you. 2 times light GBM. So another 2 slightly faster versions of, not slightly, significantly faster versions of XGBoost, but they have like a bit of a different approach to tree building, leaf growth and stuff, but I'm not going to go into details because that's kind of the future topic. So as for ensembling, so this was just one separate block. I'll denote this as green. This is block 1, and there is also a block 2, which is just separate, but a very powerful light GBM model. The same that is on the top, but only that is it's penalized during training, and it's kind of like a very strong one, but it has a smaller like final score, smaller accuracy, or smaller area under curve. And then there's of course this block 2, and you decide to ensemble this model even further, even though this is already, this blue, the notion, the section 1 is already an ensemble. It's okay, an ensemble. But you want to go further, and you just want to stack 1 and 2 together via weighted averaging, or WA. And how you do this, you have 2 options here. Either you have some certain coefficients, let's denote them alpha and beta, which lie in range of 1 and 0, and they have to sum on there's another condition, both alpha and beta. Oh no, that's pretty terrible. Alpha and beta have to sum up to 1. This kind of the restriction. You come up with such coefficients so that your final model output could be most consistent as well as most precise. And in this point, you just we can come up with like some arbitrary values for alpha and beta, namely, let's say for alpha I take 0.5, and for beta I also take 0.5. I have no choice. So this would be this would be a very balanced approach. I'll just put the scalar here. So this 0.5 times the prediction output of the first set, and 0.5 times prediction of the second set. And this would be a balanced weighted averaging, where basically we just combine the two outputs, but each model or each set of models contributes equally. This one and this one contribute equally. But in this case, this would probably, we know that this guy, this first set, is probably overfitting, because like we overtrained the model, we fed too many trees in there, etc. And we're not confident that this model is a consistent performer. In this case, we can contrast it by leveraging this LightGBM set 2, which is a single model, but we know we trained it with lots of regularization, without too many trees, without too much depth. So this is like a very consistent model. Just right here, consistent. That's also terrible. Consistent. And once you realize that, you might tweak the alpha and beta ever so slightly. For instance, you can give less weight to our first set. The first set is going to be less weight, and the second set is going to be more weight. So intuitively, from your perspective point of view, what would be the reasonable numbers to put here in the scalars for first and for second? Any ideas? If anyone's following the practice assignment or period, I guess. No ideas? No? Perhaps some potential good numbers that could work? Well, obviously, we should not take too much of this model. We should like refrain from taking more weight, giving more weight to overestimated and overconfident model, overfitted model. Which we should instead proceed to give it less weight. For instance, I don't know, 0.4, and of course this remains as this leaves us the 0.6 for a second set from LightGBM. This now gets more weight. We can, of course, evaluate this result, this ensemble of weighted averaging, and we can go further into 0.3 plus 0.7 on each of the sets and see if this does any better or maybe worse. We can, of course, fine-tune, but this is the general idea of weighted averaging, and I just wanted to stress that because it's quite important. It's a very simple technique which can win you good numbers after the after comma. Basically, not only in competition, but of course, give you even 1 or 2% score on your industry project. This is very important. There's also another type of ensembling, which is called stacking, which is basically kind of like a pseudo neural network style, but I don't like the analogy with layers. And stacking is basically a more sophisticated technique. Let me do something. Let me pull up my ensembling cheat sheet in my holy book. Because I usually mess this up, but I want to mess this up right now. Let's see, stacking. This should be here. Stacking. Yeah. So stacking, the main idea is basically to train 5 models, but this guy initially it's like the same model, but you have different sets of data. You have different cross-validation, and this whole notion of stacking, just you stack different predictions, different inferences of the model on different faults of the data, and this is pretty much how this goes. So you have cross-validation in 5 sets. You predict on the last set first, then you predict on this one. Kind of like you train on these 4, right? And then you predict on this one. Then you train on these 4, this one and this one. And you predict this one, and so on and so forth. So this one's predicted, this one's predicted, this one's predicted. So you have a completely new feature which is which consists basically only of combinations of all these different 5-folds of previous predictions from kind of different models on the same model. And the thing is, the whole idea is that you create this new feature with previous predictions. You then generalize over all 5 folds, so you do not do anything out of the ordinary. But then again, you have to predict somehow. How do you predict? You add this feature to your final model as like a simple column in your data set. So you transfer this feature into model 6. And you can, of course, do any different kind of inference techniques on the test data set. But in the end, this is just a very brief explanation and description of how stacking works. Yeah, if we went into more ensembling, there's also, of course, yeah, once again, low bias. So we're just minimizing bias when we stack. We also minimize both bias and variance when we perform weighted averaging. There's also bagging. That's just a kind of like something to add for myself. This is the idea that lowers has an aim to lower the variance instead of bias. And basically, we are supposed to create as many simple weak models or weak learners, but it's important that they have low correlation between each other so that they do not overlap. And then we just push them and put them together and press them down with a very strong meta learner, like a high capacity model. If you're trying to ensemble different logistic regressions, you might as well use like random forest classifier on top or something like that. And this basically this averages out the performance better, reducing variance, so your metrics will be more consistent and they have less like dispersion, they have much less standard deviation from the final score output. A very good technique to know as well. Yeah, there's a sampling, not too interesting. Yeah, boosting. I think we have a separate lecture on boosting. I'm not sure, but I'll just briefly introduce you to boosting. This is the popular approach. Once again, the one I just demonstrated to you here on the screen. The XGBoost and LightGBM. These are like 2 most important, most hyped libraries in data science, and I'm pretty sure some of you, or maybe all of you, encountered them, worked with them, did some projects with them, but basically they all work on a gradient boosting technique, which is namely something that has to do with, from the name, with a gradient optimization, in the first order optimization. So we have like 100 or 200, 300 different trees, the ones that you covered in the lecture, and just use you ensemble them, they predict separately, but each of these unique predictors has its weight. Kind of like similar to weight averaging that I showed once again on the screenshot, but still it's a bit different. It's more like a neural network. They all have weights, and we have a lot of iterations. Each iteration basically proceeds as follows. We receive 200, so say 200 trees. Each one of them has like some random weight, and then each tree tries to predict or just learn and predict, like train on the train set, validate the validation set, of course. And then we evaluate the performance, and if the tree performed well, we kind of increase the weights. If the tree performed poorly, we reduce the weights. We kind of assign and reassign them at each step, at each iteration. And of course, we try to outline impactful trees, impactful features, not only like trees, but single-handedly, but also the features of the data set, and less impactful. We try to like snuff these out. This is a very similar concept if you ever come across the attention mechanism, this is very similar. We just try to make use of the strongest candidates and like snuff out weak candidates or weak features. And yeah, this is also very much reduces bias. So all the powerful ensembles like boosting or stacking, they work towards reducing bias. While bagging reduces variance. Well, this was it pretty much. Do you have any questions for ensembling or any of these demonstrations? Yeah, please let me know. If not, then we'll proceed. Oh yeah, that was backing, boosting, bootstrap. Random forest, surely. Okay, so let's get to our homework, to the assignment 4. Once again, I just already opened the tasks, set up the deadlines. Once again, you have the researcher's diary, don't forget to do that. A very easy point each week on a weekly basis. But we're much more interested in assignment itself. There's a notebook, some decision tree and random forest and ensembles exercises. So let's get to it. Let's go through it. Basically, I have this opened already. Let's dive in. So decision trees in itself, the most important note in decision trees I can give to you is that they are scaling invariant. So they do not care if you have a regression task and if you give them non-normalized features. They do not care, as they just make splits individually on each feature, and they do not require data to be normalized. And that's very important to realize, because it's a very tricky question on a lot of interviews. It's one less step extra work that you can unneededly do when you do some project. You like normalize before decision tree or like random forest is being trained, and then you kind of like waste time and waste computational power. Yeah, so here we just import the same good old iris dataset and the DT classifier from sklearn API. And once again, we outline our x's and y's, and then we fit a tree. Let's see. Let me just do this. Shouldn't have done that. So let's see the parameters for our decision tree. This is kind of an important thing. Let's just go over briefly. There's of course some custom parameters you can pass for the API, but that's not important. There's a criterion, which is either Gini or impurity, which is how much. Simply put, that is, you have the decision tree, you have the nodes, and you have the leaves. And this Gini criterion tries to minimize the impurity. Sometimes the node cannot be split perfectly well, but if it is not split perfectly well, we can go further. Should probably demonstrate this on paint. Just draw a little. Yeah. So we have this decision tree, first node and second node, second level, and then we have this, that, this and that, and this and that, blah blah. But the point is, we have, like, for instance, we have a binary classification task. We have a 0 or 1 outcome. I don't know. Let's take a very unusual example, kind of like the one I despise quite a bit because I worked there. It's like whether the person is going to return your loan or not. So credit scoring application. So we have this like first very important thing. Like first, usually the decision tree here can like split the question. This will be the question: is the salary like bigger than 10,000 UAH or not? If yes, then we go right. If no, we go left. And this basically, these two nodes that formed, they are pretty much pure. But the pure by like what is meant by pure is 100% of people on the left have their income less than 10,000 hryvnias, and 100% people on the right, which is a different color, they have more or equal, greater or equal, than 10,000 income monthly. And then we go on, we just do some other, like, does this guy have like kids or something? Kids, or something else? Or if the salary is poor, is like terrible, does he have like a oh my god, I forgot the term, the collection score or something, or the credit history, like, let's just put it simply, credit history, and this is like different set of questions, and this goes on, and in the end, these nodes may not be 100% pure. There might be like a ratio of 66 to like 34 in terms of percentages on some this question, maybe some other question, and this leads us to an impure node. This is like kind of part of the model with different samples called node, has leaves, which are samples, namely. This is Gini impure, so it doesn't have Gini 0. The smaller the Gini value, the better, for optimizing, of course, the decision tree splits. There's also another criterion. So Gini just aims to make it so this impurity balance is as little as possible. So the worst outcome for Gini is 50-50. This is a worst, because both of these groups, both of these categories or classes, they are equal probable in terms of sample assignment, and the kind of like the second best case from 100 to 0, the ones we observe over here, right, is like 99 to 1. Also pretty self-explanatory, because only 1% of people actually fall out of the group, fall out of the node, and basically this is almost ideal. Like 90 over 80 is not bad, but it's not great, because you already have some impurity. And the further you move towards 50-50 balance, the worse it is for Gini optimization. There's also another metric, which is information gain, which is basically information gain. Works the same way as described in the lecture. I won't go into many details. Let's skip on. Min sample split is how many samples minimum should be for your node to be split. Defaults to 2. Minimal samples in leaf. So leaf is basically kind of a node. I use the notion node. This can also be called leaf. So also in one leaf you can have a certain amount of samples. It defaults to 1, so we can have very small leaves. But you can also have large minimal leaves, and like set the value here to 5. Weight fraction leaf is a parameter that just responds to the weight assignment on the samples on the leaf. This is usually not tuned too much, as far as I remember, as far as I'm concerned, to the best of my knowledge. The most important things are basically max features. If you want to do built-in feature selection on the decision tree, you can do that. So you can give your decision tree, you can feed there your data set with 20 columns or 20 features, like 20 independent variables, and you can set max features to 10. It'll go into basically, coming from the criterion, 10 best features. And this is built-in feature selection. Random cells. The state is self-explanatory. Max leaf nodes, it's like the limit how much the tree can grow nodes of leaves. There's also impurity decrease limit. So usually the tree algorithm will make splits only if like anytime if it leads to some good split, it will do that. But if we set the minimum impurity decrease to like 1 at least, it's going to consider, is the split we're making, the splits being these decisions, like these key intersections, is the split going to make the model look better in terms of impurity? I want to decrease my impurity. I have like 70 by 30 balance, and I want to reduce it even further. But if you want to actually fight with impurity, you have to set something here. And also, there's a limit to impurity split. If you don't want your splits to be like 55 over 45, you can set a minimum impurity split to like some certain ratio. So do not split if impurity is bigger than like 20%. Like 80 over 20 is fine, but if it's like 75 over 25, it's bad. It'll split like that. And last but not least, like CCP alpha, I don't even know what that is. We can have a look. And weights, class weights are basically something that you can assign if you have imbalanced classification problem. CCP alpha complexity parameter. Minimal cost complexity pruning. Oh, I see. This is kind of like for tree pruning, a little different technique. There should be max depth. Max depth, I think I've skipped this. And splitter as well. Splitter is like chooses the best splitting option. Max depth goes over this single most important parameter in the whole decision tree or in the forest. Is how deep can your tree go? If you set it too high, like 10 or no limit, you will 99% of the time get the overfitting model. That's very bad. You should always make sure you start with low values here, like 5 or 4 or 3, or like 7 is usually overfitting sometimes in most data sets from my experience. So this is, you have to be very careful with this parameter. All right, so what is this? Color map. Of course, we have more flowers. Now we have 3 classes. We have not only like Setosa and versicolor, we also have Virginica, virus kind, and we have like this distribution. This is basically listed color map from matplotlib, and we use the outputs. These are just random stuff for X. Yeah, this is not the tree. This is basically the very brief emulation of what decision tree looks like. We plot the decision boundary for tree classifier, pass X and Y's, and we have different depths here. We have depth 0, separates one class. Depth 1 separates the green class from the other ones. Depth 2 could also be maintained if needed, so as to understand, so as to cut off these green points. Because it's kind of tricky. Those look like outliers. They're so very close to blue class. But who knows? Maybe actually the blue petals can grow somewhat longer with less width. I don't know. So it might be very tricky here as to make this split or not. This dashed line over here and over there. But this looks pretty much as the typical result of decision tree classifier output on 3 classes. Graph is, yeah, I can read through that. So overfitting trees, yeah, this is something to be aware. So let's make some moons with 100 samples, some noise, and some random set. Let me change this to 42. Oh, I think I played with that. That's why it's 53. So we have 2 classifiers. One is completely unrestrained, just default parameters, max depth none. Then we have the same max depth none still, but we have min samples leave 4. Let's fit 2 models, and let's show 2 models outputs. So without restrictions, the model just does something very dubious. It tries to create some weird, very deep boundaries by not actually by going further in depth and not trying to optimize with like limited space, minimal samples per leaf, as the restriction is in the right picture, in the right plot. And the right one looks alright, looks pretty good. And the very sole reason for that is that we do not try to like put 0 samples, like 1 sample in the leaf. We have more than that. So each of the leaves has to have like at least 4 samples. And while this does not immediately and directly affect the max depth, but you can clearly see that this restriction on the right, the min samples leaf 4, is already kind of pre-handles the lack of maximum depth restriction, and looks to generalize quite well. What is this? Rotation problems. Okay, so angle, pi over. We make a rotation matrix, apply the dot product with the rotation matrix, x rotate it, and we have this model, just the same model that basically is tries to predict unrotated data, and we plotted the decision boundary, and it's kind of not that resilient to it, as you can see. So data just in compared to like this was the original data, the non-rotated one. This was here. This was kind of like in the middle, so top right corner. While here things have gone a bit south, and we have this decision depth 2 weird decision made. So basically, blue classes are now cornered. They do not have much space, and furthermore, like greens are all over the place and do not show the same pattern. So it kind of shows that some problems can arise from non doing additional processing of data, or non-processing the kind of like noised out data with rotations or something. But this is not really common, so do not be alerted. Last but not least, there's this these two models. One of them is on the simple model, and the other one is on the rotated model. And so the simple model basically just does, okay, bear with me, I just do one split and that's it. Pretty good, I guess. And then the rotated data, this has the same data set, the same stuff basically. It's just tries to build this ladder, the staircase, because of course you can't just diagonally split. It's not how decision tree works. It cannot do diagonal outline, diagonal split. And always, if it wants to emulate diagonal, it needs to go like this, like small splits. But this is going to be insane. So it just made two pretty clear splits, and that's about it. There's also these were classification trees, decision tree classifiers. Let's play around with some regression. Decision trees are great approximators for regression tasks. So we have the same API, but it's no longer decision tree classifier, but it's DT regressor. Pretty much has the same parameters. The only difference being the criterion. It's no longer Gini, but it's a mean square error. You can set something different like RMSE or mean absolute error. Everything else is pretty much the same. So here we have this showcase with two different trees. One has depth limit 2, the other has depth limit 3, and some randomly generated data. Let's see. So this is how the decision tree approximates regression. It just tries to build this very funny staircase on your like parabola or whatever that's supposed to be. So this is kind of a bit weird and a bit awkward, but still it does a good job of it, I guess, at least in these pictures. And from what I can tell, max depth 3, like more depth, is slightly better approximation, certainly better fit than max depth 2, as like the curves of these staircases, they kind of align over data, and they could be prone to actually much better and exact predictions inference on the task set. While on the left, the models has too little variance and too much bias, and namely it's underfitting. It has very big depth restriction, but still it tries its best to kind of like approximate this parabola, this polynomial function. Yeah, this is basically how it looks like under the hood. There's also more. We can introduce once again our test with min samples leave, set it to 10 here, and 1 is not restrained, the second tree is restrained. We fit both of them, generate some data, predict, and plot everything. Let's see. What have we got here? Oh yeah, this is a very good example of typical 100% undoubted overfitting. What's going on here is on the left we have no restrictions on the tree, and the tree's like, okay, I can do whatever I like, and basically it just creates all these chaotic patterns with like weird stairs. It's not even stairs anymore, it's like more like knitting, like your grandma tries to knit your sweater. This is what happens, all these like chaotic patterns, and this just tries to completely include every single point into your into its approximation, and this never generalizes well, of course, as you may well know. Whereas if you look on the right, in the right, like the right hand side, there's a min samples leave 10 limit, and 1, 2, 3, 4, 5, 6, 7. The depth here is somewhat about 7, 8. It's much better. It's obviously restrained. It has this like in each leaf, each split has to have like at least 10 samples in the leaf. And what this means is it kind of like preemptively restricts the depth, and it approximates this parabolic function absolutely nicely. Like as far as I'm concerned, it's like even better than some polynomial regressions in some way. But I'm not going to go further into this. This is basically why you need to be careful and not to forget to do like at least do some max depth restrict or min samples leave. The parameters here in these models, in contrast to SVM, in contrast to logistic or linear regression, parameters here start to matter. So please be mindful. There's also about ensembles. I'll speed up a bit. Ensembles, yeah, let's make some more moons. And we have this, there's a sklearn.ensemble module, which has like all the bagging, stacking stuff that we talked about. It usually has bagging classifier. So by bagging classifier, we can obviously see that it's kind of like sort of a pipeline. So we pass a decision tree inside, the one that we just created. We pass number of estimators, so number of how many such trees you want to grow, how many samples. What is this? What samples? Sorry. A bit lost here. Samples. Oh, okay. So basically, this is how much the model, the general bagging model, leaches from the initial data set. And each iteration, it just takes 100 samples. Okay. Yeah, you can of course look through the documentation for bagging classifiers, but it's nothing too fancy, honestly. So you pass max samples, which you want to draw from the X distribution, the original data. If you want to make bootstrapping, this is what you've been explained in a lecture. I'm not really great at explaining bootstrapping, but I can try. Basically, bootstrapping just signifies the replacement, so if we can take the same sample or not. Or if it's false, we do not perform replacement. If it is, we perform replacement. And then we just train this CLF bag classifier and predict. And see the accuracy, pretty good, 0.9, not bad for the moons. And then we train a tree, decision tree classifier, single tree, random state 42. See, we do not restrict anything here, do not like put max depth or anything still. We have random state 42, we just train a single model, and boom, it gives us a worse result. This is because 500 heads like are much smarter than one head, or like Гуртом батька добре бити, something like that. So this is basically a very intuitive concept in machine learning as well. So you can you should get better ensemble. If you have an opportunity to make an ensemble, you should do it. Do not leave out the single model, unless like it's restricted by the industry restrictions or something. Then we have this color map. What is this? Oh, that's just a function. And then we have the decision tree. Once again, we didn't restrict the tree. It's terribly overfitting, as you can see, like this weird pattern here, this pattern here on the 1.5 axis. There's also this weird island here and some cut things placed in there, but the decision tree from bagging, 500 different trees grown, it looks like a very smooth curve, as if this was like some logistic regression or something like that. But slightly more spiky, but still we can relate to that. These were not these individual models could have been overfitting as well, like this one on the left. But in the end, we got a pretty decent kind of like separation of classes, and this looks cool. There's also random forest. So what is this? So just define a backing classifier with random splitter, not the best, but random, with certain leaf loads restriction and max samples fraction, and we bootstrap, of course, and we train predict in the same data. And then we import from the ensemble module again the RF classifier, a random forest. We pass 500 trees in there, and the same restrictions as they were introduced here, just max leaf node 16, nothing else. Let's train. Trains pretty quickly. And what is this? Yeah, obviously they look pretty similar, the outputs. If this number was 1.0, the outputs would be exactly similar. But it looks like there is some difference still. Probably random classifier, RF classifier is better, working than decision tree with random splitter. So don't use that API. I urge you to use this API. There's also some more tests on the regressor or this classifier, and we from random forest. This is like the first model basically that can have such thing as like the model object can have a feature importance attribute, and if you look into it, you just iterate over name and score. This is fine, but if you look at the feature importances, these are basically the coefficients on how much each of these 4 features contributed. So the least important thing was sepal width, only 2% importance. Then goes sepal length, slightly more important because one of the classes is well separable by it. And then there is petal length and width. These are 2 most important. So just don't look into sepals, mostly only into petals in this task. It's like 42%, which is quite insane. Let's see the demonstration. Decision tree classifier, and this with replacement. Yeah, well, there's some more showcasing of you how sometimes it makes weird stuff. Decision trees are very preferred model because they're easily explainable, but sometimes they do weird things. That's all I can say. This is the voting classifier, obviously, something I've mentioned at the start of the period. Let's make some more moons. There's a random forest classifier, through our just RF method, the VC classifier, just VC or voting classifier, and we also use logistic regression in SVM. We train all these models. First we initialize them. Log regression, you know, SVM you also know, or this is the classifier, it's not SVM, it's VC, kind of, and random forest. So there is a hard voting concept where you just call this voting classifier. You explicitly define tuples as a list of tuples of name for the model and its object. And then you specify voting hard. What is voting hard? Let's see. voting can be hard or soft. It defaults to hard. So if hard, basically, we need the majority rule to give out the class to the sample. If there is soft, it's a unusual, less common. Let's say it's that way. Less common way to vote. Then we use argmax of the sums of predicted probabilities. Basically, taking the most likely class from the sum of the post. Like in neural nets would be softmax, but just from the probabilities themselves. And they even specify this way is recommended for an ensemble of well-calibrated classifiers. So if you have something messy, if you have like 500, no, you have like 5 or 3 ensembles, and they are like you're not confident they're good, then it's probably best to use hard voting. Else, if you know they're like consistent, well-trained, robust, and stuff, then you might as well use soft. It's gonna be better. And let's wait. Yeah. So voting classifier, just make a voting classifier like that. Voting hard. You fit the pipeline, and then let's see each individual one and the voting averaged. So in our binary classification task with the moons, log regression was least performing, 86.4% accuracy, or was the accuracy? Random forest was just as good as SVC by like 89.6 percent accuracy, and the final voting classifier, which voted hard, had an accuracy, the best accuracy overall, like 91.2%, pretty good. Whereas the soft voting, the same example, logistic regression, LBFGS is one of the solvers. You just do the same vote soft, and let's see the scores. Here, basically, the results are even better, apparently. Kind of like the individual models do not differ too much, but the voting has like the 0.08 accuracy increase, which is not bad. It makes it a nice little round 92%. And then pretty much that's it as for ensembles, trees, random forest, etc. Let's quickly summarize your, look through your homework assignment. So you're asked to make the same thing, basically work with moons dataset with just very simple import make moons, number of samples, noise. You have to then split it into train and test splits. Basically making a simulation of a full project, like data science analysis or like modeling. You can obviously, I do not require you to make a train validation test, but if you want to, it's a very good practice, I guess. Very good touch to it, because usually you do not like immediately test on test, you test on validation. Up to you. And then using grid search or invite search or maybe something else that you know of, you are supposed to fine-tune the decision tree classifier model. And fine-tune meaning you just need to pass a dictionary with all the relevant to in your opinion, values of hyperparameters, like max depth, min sample sleeve, min sample split, impurity splits, etc., and just optimize it. And yeah, please also specific ask of you is to try different values for the max leaf nodes parameter. Nothing too fancy here, just all that. There's also an exercise 2 to download MNIST. You've been working with it, right? Yeah, I think so. I should think so. Of course you have. So you have MNIST already, I think. If you don't, please download it. And there's this task requires 3 splits: train, validation, and test. 50, 10, 10. Then train different models on them, on these splits. The random forest, the logistic regression, and the SVM. Then you are supposed to do some pseudo ensembling, make voting classifier. It could be hard or soft, up to you. Then you train a new model, completely new, doing basically stacking something I showed here. Oh no, it's no longer there. Doing stacking and predicting on validation set, and saving these predictions, and then merging these predictions. This is going to be a new feature for the train set for the new model, and then you are supposed to test it on the train, and then you test it on the set, on the test set. And basically, yeah, you perform stacking. You can Google it up. You can ask questions, like ping me up on Slack or Telegram. But this is not that complicated. You're supposed just to make a good validation and save all the results. Inference on different splits. And this is pretty much it. There's not much to it. You have more than enough capacity to like solve these without a problem right now. So I don't think there is any point into additional showcasing for the how to solve these assignments. Yep, that was it. Once again, we're a bit earlier today. Any questions? The recording will be available very soon, very shortly. Hope everything is clear. I'll take silence as a yes. Such a case, I did open the home task, home assignment. Please do not forget to like upload them, and sometime soon I'll check them. If no questions are further available, then I wish you all a good and productive week, and stay safe. And yeah, bye bye.
Bye bye.
Goodbye.